Hello everyone, welcome to IIT and GATE classes. This is lecture 21 on TOC and most probably this is your last lecture. That is, in this lecture I am going to complete your TOC subject. Okay, so I am starting from the point where I have left in the lecture 20. So please watch my lecture 20 for proper understanding. Okay, so in this lecture, our first question is sigma star CI or UCI. Okay, if just to revise, I was discussing countability topic, and in countability, I have discussed mathematical part, that is set of real number is uncountably infinite, set of natural number is countably infinite, set of integers is countably infinite, set of rational numbers is countably infinite, and so on. I have discussed all these things. Now I am jumping to TOC, and our first question is question number 1. Your first question is sigma star is CI or UCI. How will you prove it? Okay, so this is sure, this is for sure that sigma star is infinite. Okay, you already know this fact that sigma star is infinite, but it is countably infinite or uncountably infinite. This is our question. So I will prove in a very simple manner. I will say, see here carefully, I will say, let us suppose sigma is 0, 1. Okay, or in fact, you can take any finite alphabet. It hardly matters to me. Sigma star will be what? Say null 0, 1, then 0, 0, 0, 1, 1, 0, 1, 1, then triple 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, dot, 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 up to infinity. Okay, like this we write sigma star. So sigma star is nothing but all possible strings over 0 and 1. Okay, so let me label like this. Okay, so I will say null is mapped with natural number 1, 0 will map with natural number 2, this is mapped with natural number 3, then 4, then 5, then 6, then 7, then 8, then 9, then 10, then 11, dot, 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 like this. Okay, so in fact I have written sigma star in such a manner so that I can map it with natural number set. Okay, so this ordering is known as proper ordering. Okay, so I have written sigma star in proper ordering. So what is the exact meaning of proper ordering? In proper ordering, we write the string lengthwise, and while writing the string lengthwise, we will write the 0 first and then 1. Okay, so like see here, null 0 length string, then 1 length string 0, then 1, then 2 length string. For 2 length string, I will write double 0 first, then 0 1, then 1 0, then 1 1. Okay, now 2 length string are over. Then 3 length string, I will start with triple 0, then double 0 1, then 0 1 0, then 0 1 1, and so on. Okay, so I hope I have made the point clear. So directly and directly, what I want to say is I'm not going into pretty much details because this is a basic course. So you just try to remember the fact that sigma star is countably infinite. Why it is countably infinite? Because I have established one-to-one correspondence between the natural number set and the sigma star. Okay, so pictorially I can say like this: 1 2 3 4 dot 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 dot, dot up to infinity. This is your natural number set, and your sigma star will be null 0 1 0 0 0 1 dot 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 dot, dot like this. Okay, so 1 will be mapped with null, 2 will be mapped with 0, 3 will be mapped with 1, 4 will be mapped with double 0, and so on. Okay, so I have established one-to-one correspondence between natural number set and sigma star. Hence, this will be countably infinite. Okay, please try to remember this fact. This is countably infinite. So sigma star is countably infinite. Okay, so let me put everything on one slide so that you can note it down properly. Yeah, please note it down. I am jumping to next slide now. Now, next question is 2 power sigma star is UCI or CI? Okay, if you remember the Cantor's theorem, I have already told you that 2 power countably infinite set is always uncountably infinite. And sigma star is what? Sigma star is countably infinite. Hence, 2 power sigma star will be uncountably infinite. So please try to remember this fact. The 2 power sigma star is uncountably infinite. Now, what exactly is 2 power sigma star? 2 power sigma star is set of all subsets of sigma star. Now, set of all subsets of sigma star. See here carefully. 2 power n was what? Set of all subsets of natural number. So 2 power sigma star will be what? Set of all subsets of sigma star. Okay, why I am calling it as like this? Because it is nothing but power set. Okay, so if S is a set, 2 power S is what? Set of all subsets of S. So similarly, sigma star is a set. So 2 power sigma star will be what? Set of all subsets of sigma star. And any subset of sigma star is what? Now please try to listen carefully. Any subset of sigma star is what? Language. Any subset of sigma star is nothing but a language. So Directly, indirectly, what I want to say is set of all possible languages. Let me write it in a different color so that you can note it down carefully. Set of all languages over sigma star. Set of all languages over sigma star is uncountably infinite. This is very, very important point. Please note it down carefully. Okay, set of all languages over sigma star is uncountably infinite. So directly, indirectly, I have proven this fact. Now let's jump to next question. Next question is set of all Turing machines is countably infinite or uncountably infinite? Set of all Turing machines. Okay, so how will you approach this type of question? Let me tell you a brief background. Okay, so in Turing machine, we have delta moves, like Q0 A goes to Q1 B R and so on, like this. We have moves. Okay, and each and every move can be encoded in a binary format. How? Let me say Q0, I will label Q0 as single zero. Okay, then comma will be as a separator. Now A will be treated as say single zero, then as a separator. Then Q1 will be treated as double zero. Then B will be treated as double zero. Then left and right, we have two possibilities now. So left will be treated as zero, R will be treated as double zero. Okay, so this is a single move for this is a binary number for this move. If you are not able to understand, let me tell you properly. See, we have set of states now. So Q0 is 0, Q1 is double zero, Q2 will be triple zero, dot, 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 dot. Okay, and input your tape alphabet. A will be treated as 0, B will be treated as double zero. If you have C, then it will be treated as triple zero, dot, 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 dot. Okay, left direction, direction left is 0, right is double zero. Okay, like this. We have moves like we have encoding like this. Okay, so Q0 will be Q0 is labeled with 0 now, so I will label it as 0. Then 1 will be treated as a separator, then A with single 0 and so on. Okay, so I have explained this this move. Okay, this move of Turing machine can be encoded by a binary number. Why I am doing so? Please have patience. I will come to this point also. But let me tell you something like this. Okay, so I hope you have got this point. Now I will write double one. Double one means next move. For next move, say I have a move like say delta Q1B implies Q2CL. So this move will be, so after double one, I will write this. So Q1 is nothing but double zero. See here carefully. See here, Q1 is double zero. Now. Yeah. So double zero, then I will have one as a separator. Then B is double zero. Then one as a separator. Then Q2 is triple zero. Na? So Q2 is triple zero. Then one as a separator. Then C is what? Triple zero. Then one as a separator. Then left is single zero. So this is another move and so on. Okay, so we will have double one and then we will have move and so on. Okay, so directly what I want to say is each and every Turing machine can be encoded as a binary string like this. Okay, this is a of course this is not a complete Turing machine, but I'm saying you, I'm just giving you idea, or I'm just giving you a hint that each and every Turing machine, the bottom line is each and every Turing machine can be encoded as a binary number. This is the bottom line. Okay, this is very, very important point. Now see what I will say. Each and every Turing machine can be encoded as a binary number. So if you collect set of all Turing machines, that will be just like a obviously infinite set. That will be a infinite set, and in that set, what we will be having? We will be having strings like this. This is one Turing machine. This is one Turing machine, and another Turing machine, and so on. We will have strings like this. Big strings, but it hardly matters to me. We will have a binary strings. First string, then second string, then third string, dot 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 dot, like this. Now see carefully. This is what? This, let me set of all Turing machine, let me say it as a L. Now L is what? Subset of sigma star or not? Sigma star is what? All possible strings over 0 and 1. If sigma is 0, 1, if sigma we take it as 0, 1, sigma star will be what? All possible strings over 0 and 1. L will be subset of this, and L is what? Set of all Turing machines. So directly, indirectly, what I'm saying is set of all Turing machines will be countably infinite. Why? Because every subset of countably infinite set is countably infinite. I have already told you in the previous class. So hence, set of all Turing machines will be countably infinite. This is very, very important point, and it has been asked many times in GATE as well as UGC-NET exam. Please try to note it down carefully. So set of all Turing machines is countably infinite. Okay, yeah. Now I want to tell you one more important thing. Please see here carefully. See, let me say like this. This is set of all Turing machines, and this is what countably infinite set. And this is set of all languages over sigma star, that is nothing but 2 power sigma star, and 2 power sigma star is UCI, and I have already told you that UCI, uncountably infinite set, is much larger than countably infinite set. So directly indirectly what I want to say is these all are your Turing machines and these all are your languages. So there is no one-to-one correspondence between Turing machines and languages. That is, there are lots and lots of languages which cannot be accepted by Turing machines, and hence we call them as non-RE languages. Non-RE languages. So no, why? So if anyone says that why non-RE languages exist, you will directly say the set of all Turing machines is countably infinite, but set of all languages is uncountably infinite. Hence, there is no one-to-one correspondence between countably infinite and uncountably infinite set. So set of Turing machines are very less, but set of languages are very large. So directly indirectly, what I want to say is there are lots and lots of languages which are not accepted by your Turing machine, and we call them as non-RE languages. Okay, so I hope I have made the point clear to all of you. Okay, now let's jump to the next slide. Yeah, so set of all known, now this is a very good question. Set of all known RE languages uncountably infinite or countably infinite? So you can directly answer it. See here carefully. 2 power sigma star, 2 power sigma star is nothing but set of RE languages union set of non-RE languages. Okay, non-RE languages obviously na. See, entire set is divided into 2 parts na. One is RE and another is non-RE. So RE languages, obviously set of all RE languages is what? Countably infinite. Why countably infinite? Because language is said to be RE when we call languages said to be RE if there is a Turing machine accepting it, and set of all Turing machine is countably infinite. So each Turing machine corresponds to each RE language. You can directly indirectly say like this. So there is one-to-one correspondence between Turing machines and RE languages, and set of all RE languages is countably infinite. I'm not going to repeat it again and again. Please, if you are not able to follow, please rewind the video and watch it again. So directly and indirectly, I have proven you that set of all RE languages is countably infinite. So I will say here, this is countably infinite, and this we already know it is uncountably infinite. So what can you say about it? It should be uncountably infinite. If you are not able to follow it, please watch my previous lecture. I have given you proof about why non-rational numbers are uncountably infinite, like this also. And so we said that real numbers are nothing but rational numbers union irrational numbers. So rational numbers are countably infinite. Okay, and this is UCI. You already know this is UCI. So this should be UCI only. So please note it down carefully. I'm jumping to next slide. Okay. Now each non-RE language is CI or UCI. This is very good question. Please try to follow it. Set of all non-RE languages is UCI. I have already proved. Next question is each non-RE language. You pick one non-RE language and you say it either it is CI or UCI. So obviously it will be countably infinite. Why? Because each and every L is subset of sigma star. This L can be RE or it can be non-RE. Any language, it can be any language, and any language is subset of sigma star. And sigma star is what? Countably infinite. So directly indirectly L will be what? Countably infinite. Okay. So it hardly matters. Whatever language you pick, it will be always countably infinite. Please note the point. Jumping to next slide. Yeah. So now countability topic is completed. We are jumping to your seventh topic according to syllabus of your chapter 4, that is Turing machines and decidability, and that topic is problem and language corresponding to problem and so on. So see here carefully. I have written all the things before so that lot of time can be saved. So what is a problem? Informally, problem can be referred to questions. So what is a problem? Problem is nothing but questions. Questions like Is the given context-free grammar ambiguous? Is the language generated by grammar finite? Does two context-free grammar generate same language? And so on. All these are questions. So these are nothing but problems. So if I want to name this problem, I will say it as ambiguity problem of CFG. I will call it as ambiguity problem of CFG. If you want me to label this, I will say, is the language generated by grammar finite? So finiteness problem. This is known as finiteness problem. Finiteness problem. Anyway, please don't worry about these names. I am going to tell you about each and everything in pretty much detail. Okay. Next is, does two context-free grammar generate the same language? So it is nothing but equivalence problem. This is equivalence problem of CFG, context-free grammar. So problem, I hope you have got the idea. Problem means what? Informally. I'm not going into formal details. I'm just saying you informally. It refers to questions. Questions like, is the given CFG ambiguous and so on. Please note it down carefully. Instance of problem. Next definition is instance of problem. Instance is what? A grammar is given and you try to find is it ambiguous or not. Okay. So these are the problem. These are general thing. Now, if I take this CFG ambiguity problem of CFG, I will say, I am giving you a grammar. Now tell me, is it ambiguous or not? So that is known as instance of problem. Like a grammar is given and you try to find, is it ambiguous? So this is instance. Like say, I have given you instance like this. This is an instance. I have given you a grammar. Okay. Yeah. So instance can be of two types, yes instance and no instance. Yes instance means what? See, this is an ambiguous grammar. Na? So I will call it as yes instance. Okay. I hope you already know why it is ambiguous and so on. Try to generate two or more positive for null itself. You will get your answer. Okay. And it is no instance. This is unambiguous grammar. So instance means what? Given you have given a grammar and you are trying to find, is it ambiguous or not? Instance are of two types, yes instance and no instance. Yes instance means what? Ambiguous grammar, and no instance means what? Unambiguous grammar is given. Okay, so I hope I have made the point clear. Next, relationship between language and problem. This is very, very important point, and most of the students get confused in this point. So let me clear it properly. Language is set of all yes instances of the problem and coded in binary. Please note it down carefully. There are two keywords here: yes instances and coded in binary. So now you may wonder that, sir, how ambiguity problem of CFG will be encoded in binary? There is no problem at all, just like Turing machine. So, and there is no fixed rule and regulation that you have to encode in binary format in this way only or in that way only. There is no rule and regulation. So I'm just giving you a hint. S implies AS or null. Okay, so I will say S is represented by single zero. Okay, then A is represented by double zero. Then S again obviously single zero, and null is represented by triple zero. So I will say S implies AS now. So S, then one as a separator, then A as double zero, then one as a separator. Okay, so now move is over, then you may apply double one. Your one production rule is over. Next is S implies null. So S is what? Zero, then one as a separator, then null is triple zero. That's it. So this is the binary encoding for this grammar. And again, I'm repeating, there is no fixed rule and regulation about how you convert it into binary. The main idea is you can convert it into binary. That's it. I just want to give you intuitive idea that we can convert any grammar into binary. That's it. So you may give any problem to me. I can convert it into binary like this. Okay. So a language is what? All yes instances of the problem encoded in binary. So ambiguity problem of CFG. So L will be how? L will be what? L will be all the ambiguous grammars, all the context-free grammars which are ambiguous, like this. This is ambiguous, na? So you will encode it into binary and write it here as a string. So let me suppose that the string becomes this only. Okay, so 0 1 0 0 double 1 0 1 triple 0 and so on. Okay, so all these will make a language. So I hope I have made the point clear. So language is what? All the yes instances of the problem encoded in binary. Please note it down fastly, and I'm jumping to next slide. Yes, so next slide is problems are of two types. One is optimization problem and second is decision problem. Optimization problem is finding problem. That means you want to find something. And decision problem is yes or no. That means output is either yes or no. That's it. So this is known as decision problem. Okay, as the name implies, decision means what? Yes or no. So that's it. So decision problem example is the given CFG ambiguous? So you have given a CFG, you want to find is it ambiguous or not. So this is a problem. So answer may be either yes or no. That's it. This is decision problem. Now this corresponding to this decision problem, optimization problem will be what? Find a string W belong to LG such that it has two or more passphrase. So I hope I have made the point clear. So hence every decision problem has optimization problem version and vice versa. So these two are interconvertible. Okay. And in TOC subject, we will concentrate on decision problems only. Please note it down carefully. I'm jumping to next slide. Yeah. So now see here carefully. So decision problems. So I have already told you in the previous slide itself that we will concentrate on decision problems. We are not jumping into optimization problem because these are interconvertible. Okay. So decision problems are of two types: decidable and undecidable. Decidable means language corresponding to problem is REC. This is very, very important point. Please note it down carefully. Okay. So I am underlining the keywords. Language corresponding to problem is REC. Then we will call that problem as decidable. And I have already told you what is the relationship between problem and language. Okay. So language is what? All the yes instances of the problem and coded in binary. Okay. What is undecidable? Language corresponding to problem is RE, but not REC or non-RE. Okay. RE, but not REC or non-RE. So directly, indirectly, I want to say that language corresponding to problem is not REC. That's it. Okay. So see here, if you are able to remember, see here carefully. This is REC, set of all REC languages. Then this was set of all RE, and this entire set is non-RE. So let me label it. This is 2 power sigma star, na? 2 power sigma star. So all these languages here, all these are non-RE. Non-RE. Okay. And here, these are what? These are RE, but not REC. And these are what? REC. Please note it down. Okay. So what I'm saying is that if you are either here or here, okay. So like this here, all these area, this correspond to undecidable problems. That means language corresponding to problem is RE but not REC. See here, RE but not REC or non-RE. Or indirectly, you will say that a language corresponding to problem is not REC. That's it. If language corresponding to problem is not REC, then it is undecidable. Decidable means language corresponding to problem is REC. Okay. So indirectly, it also means that there is this algo which always say yes or no. REC means what? There is this algorithm which always say yes or no. And undecidable, no such algorithm exists. Okay. Now examples is the given number prime, is the given number perfect, and so on. Obviously, you know all these things that these are decidable problems. And what is the way to judge that this is decidable or not? Just try to imagine if you are able to write program for the problem, then it will be decidable. Like given number prime or not. Obviously, you can design a program in computer. Is the given number perfect or not? Obviously, you can design a program. Perfect means what? Perfect number is sum of all the factors is equal to the number. Like 6 is a perfect number. 1, 2, and 3. These are the factors less than 6. Positive factors less than 6 are 1, 2, and 3. Sum them up, you will get the 6. This is a perfect number. So obviously, you can check it out. The given number is perfect or not, given number prime or not in a computer itself. So it is a decidable problem. These are examples of decidable problem. And undecidable problem examples are ambiguity problem of CFG, equivalence problem of CFG, and so on. There are lots and lots of examples. We will study them. Don't worry. And see here carefully. I've said no such algorithm exists. No such algorithm exists means ambiguity problem of CFG. To solve this problem, nobody in this world will ever be able to write a program for algorithm for it. Okay, nobody in this world will ever be able to write algorithm for it. This is a very strong statement, and it has been formally proven also. Okay, so please do not think that today, tomorrow, today or tomorrow someone is not able to write, but someone may be able to write algorithm for it after 100 years or 200 years and so on. But it is not the case. I'm telling you a very strong statement. Nobody in this world will ever be able to write algorithm to solve this problem. Please note it down carefully. When a problem is undecidable, nobody in this world will ever be able to write algorithm to solve this problem. Okay, say it like this way. So I hope I have made the point clear. So please note it down carefully. I'm jumping to next slide now. Please note it down carefully. Yeah, so problem for which you can make program in computer and get answer yes or no are decidable problem. This is you can say intuitive idea about how will you check problem is decidable or not. Okay, if you think that you can make a program, then obviously it will be decidable. Okay, that's it. And it's obviously informal way. I'm not going into details. I'm just giving you a idea, or you can say intuitive hint, that how can you say problem is decidable, like this given number is prime or not. Obviously it is decidable perfect or not. Obviously decidable finding factorial of a number and so on. Okay, so just I'm not going into detail. That's it. Okay, so next. So see, this is the summary. Okay, this is very important point. Please note it down properly. Okay, so problem is decidable. Problem is decidable means L is recursive. Language corresponding to problem is recursive, or there is just halting Turing machine accepting L, or there is just algorithm. These all are one and the same thing. Please note it down carefully, otherwise you will get confused. So when can we say problem is decidable? If L is REC, or you can say there is just halting Turing machine accepting L, or you can say there is just algorithm. Next, problem is undecidable. When can you say problem is undecidable? L is not REC. That's it. L is not REC, or there is this halting Turing machine accepting L. So there is no halting Turing machine accepting L, or there is no algorithm. That's it. Okay, so then you will say problem is undecidable. Please note it down carefully. Yes, so now I'm jumping to some problems. First is membership problem. Membership problem is given some language L and an arbitrary string W belong to sigma star. Does W belong to L? This is the problem. Okay, so we have a language. And a string W, and I want to check W belong to L or not. So this is the membership problem. For regular, DCFL, CFL, CSL, REC. Or for all these, this is decidable, but for RE, it is undecidable. Okay. Why for RE it is undecidable? I'm not going into details. I'm just telling you that for all these languages, it will be decidable, but for RE, it will be undecidable. Okay. So just try to remember this. And I'm not going into pretty much details because this is a basic course. Okay. In advanced course, I will give you proof and all these things, but I'm just giving you hint here. Okay. Please note it down carefully, and I'm jumping to next slide. Next is emptiness problem. Is the given L empty? This is the problem. Okay, is the given L empty? This is the problem. For regular, it is decidable. For DCFL, it is decidable. For CFL, it is decidable. But for CSL, REC, and RE, it is undecidable. Okay, so how will you check it? See, I'm just giving you intuitive idea. I have already told you about reduction of CFGs. Do you remember this? If you are not able to remember, please watch my previous lectures. Reduction of CFGs. Okay. In that, I have told you about useful and useless symbols. Now, if you say that S itself is useless, then we will say that LG is equal to 5. And this is what exactly we are saying. Is the given L empty? Okay, and let me tell you one more thing. Membership problem. In membership problem, I forgot to say one thing. Sorry for that. See, decidable means what? There is this algorithm. So this language may be infinite also. So how will you give infinite language to an algorithm? Exactly what membership problem means is, see, MP algo, membership algorithm. So to this membership algorithm, I will give two things. First is L and second is W. It will say yes if W belong to L. If it will say no if W does not belong to L. No when W does not belong to L, and yes when W belong to L. Now the question is, to this algorithm, how L will be given as input, because L may be infinite also. So for that, we will use representations, finite representations. Like if L, you can say if L is regular, then you will say in place of giving entire language, we will give FA, or you will give regular grammar, or you will give your regular expression. Okay, if it is CFL, then you may give PDA, or you may give context free grammar, and so on. Okay, so similarly here also. So is the given L empty? So if so again the same question will come. Emptiness algorithm, emptiness algorithm. You are giving L and you are giving W. Okay, or see, directly I'm giving L. Okay, and it will say yes or no. Yes means what? L is empty. And no means what? L is not empty, or L contains some string. Okay, So for no answer, it is obvious you may give language directly. But if language is empty, then how will you give this language? There is no string in that language. So how will you give nothing to an algorithm? So for that, I'm saying that I will give representation. Okay, so directly and indirectly in each and every problem, I will use a finite representation of language. Okay, in each and every problem, we will use finite representation of language. Finite representation of language. Okay, so if regular, then we will use FA, or if language is CFL, then we can give PDA and so on. Okay, yeah. So and you don't need to think about how exactly these algorithms will be made. How will you give PDA to algorithm and so on? Please do not think about it. Okay, it's out of scope. Okay, so that's it. So for emptiness, yeah. So I was saying that reduction of CFG, I have said that if S is useless, then LG will be 5. So in place of giving L, you will give CFG, CFG or PDA and so on. So I will say that I will apply algorithm and say that if S is useless, then I will say that language is empty, otherwise it is non-empty. So useless, useful, till context-free grammar it was allowed. So till CFL, it will be decidable. But for CSL, REC, RE, it will be undecidable, because there is no such algorithm of finding useful, useless in CSL, REC or RE. Okay, I hope I have made the point clear. Okay, so CSL means what? Directly and indirectly, I'm talking about context sensitive grammars and so on. Okay, so I hope I have made the point clear to all of you. So this was the intuitive idea about why emptiness problem is undecidable for CSL, REC and RE, and why it is decidable for why it is decidable till CFL. Okay, so please note it down carefully. I'm jumping to next slide. Yeah. So next is completeness problem. Completeness problem means what? Is L is equal to sigma star? So I need to check this thing. So here again, we will give a finite representation. I am not giving language itself because sigma star is infinite. So how will you give infinite language to any algorithm? Okay, so I will use finite representation. That means for regular, I will use FA. For CFL, we will use PDA and so on. So you have to just remember the fact that for regular and for DCFL, it is decidable. For rest, it is undecidable. Okay, yeah. So next is equality problem. Equality problem means what? Given two languages L1 and L2 of same type, is L1 is equal to L2? That means are these languages same? So obviously I'm not going giving language. I will say that FA1 for regular. I will say we have two FAs, FA1 and FA2. So does they accept the same language? This is the question. Okay, so this is equality problem, and you have to remember for equality problem, regular and DCFL both these are decidable. For rest, it is undecidable. Okay, yeah. Next is disjointness problem. Again, same type of problem. Given two languages L1 and L2 of same type, is L1 intersection L2 empty? Okay, so directly and indirectly, I will say that we have FA1 and we have FA2. So does their intersection will give us empty language, or does their intersection will produce a FA which will accept empty language and so on? Okay, so this is a question. And for regular, you will have to remember that disjointness problem for regular is decidable, and for rest other it will be undecidable. For rest it will be undecidable. Next is finiteness problem. Finiteness problem says, is the given L finite? So finiteness problem, again, it will be decidable for regular, DCFL and CFL. For CSL, REC and RE, it will be undecidable. Okay, so how will you prove? So I'm just giving you hint. So see here, like if we say S implies AS or null and so on. So I will say that there is a recursion, so it will produce infinite language. So there should be no recursion like this. So for till CFL, we will be able to guess like this, but for CSL, we may not be able to guess. But you will say, you may argue that, sir, see here, you can say A is giving us A like this. So obviously, sir, there is a recursion, and this is a move of context sensitive grammar. So you may say that language will be infinite and so on, but we do not know about this A is useful or useless. We do not know it. If this A was useless, then obviously this recursion is meaningless. Okay, so it won't produce any string. Okay, so that's it. So I have just given you a hint, and these hints are really not required. You just have to remember a table, and I will give you a table in the end. So don't worry about it. Okay, so finiteness problem. Regular, DCFL, CFL, it is decidable. For rest, it is undecidable. Next, subset problem. Given two languages L1 and L2 of same type, L1 subset of L2. This is the problem. So for subset problem, only regular it is decidable. For rest, it is undecidable. Okay. Yeah. So next is regularity problem. Is the given L regular? This is the problem. So obviously this question will be trivial for regular. Given L is regular, then obviously it is regular. So for regular, it will be decidable. This is a trivial question. And for rest other, for DCFL also it is decidable, but for rest other, it will be undecidable. Please note it down carefully. Next is ambiguity problem. Is the given L ambiguous? This is the problem. So for regular, it will be decidable. For DCFL, it will be decidable, but for rest, it will be undecidable. Okay. So and I want to clear one thing. Is the given L ambiguous? I'm saying it language ambiguous. Okay, so language may be ambiguous or it may be unambiguous. So when a language is ambiguous, when we are not able to write unambiguous grammar for it. Okay, so let me tell you one thing. L is ambiguous. L is ambiguous if and only if no unambiguous grammar, no UA means unambiguous grammar, can generate L. Can generate L. Okay. So for regular, it will be decidable. For DCFL, it will be decidable. But for rest, it will be undecidable. Okay. So why it will be? See, regular, it is a trivial question because for regular, we have a DFA and DFA can be converted to grammar and that grammar will be unambiguous. So obviously, each and every regular grammar is unambiguous. Similarly, the case is with DCFL. For DCFL, we have DPD and DPD is just like DFA. So obviously, it will every DCFL will be unambiguous. But CFL may be ambiguous or unambiguous. For example, like this. A power n, B power n, C power m, union A power n, B power m, C power m. So if you want to generate string A power, say A power 2, B power 2, C power 2, this string will be in this language also and this language also. So this language will be ambiguous language because we cannot write any unambiguous grammar generating it. Why we are not able to write unambiguous grammar generating it? I have given you a small hint. Like this string first language is saying A and B should be equal. Second is saying B and C should be equal. So if A and B, C, so if A, B and C all are equal, then obviously we will have two paths. Okay, so for example, see here, S1 is generating this grammar. Sorry, S1 is generating this language, S2 generating this language. Okay, so if you are not able to follow, then watch my construction lectures, construction of context-free grammar. You will get the idea. And I have, by the way, I have already explained you this example in construction itself. So S1 is generating this, S2 is generating this, and I will write S goes to S1 or S2. This will be for the union. For union, I will say S goes to S1 or S2. So S1 will generate this language, S2 will generate this language, and S goes to S1. S1, S2. Sorry. Yeah. So S goes to S1, S2. Yeah. So for this string, S1 obviously will generate this and S2 will generate this. So obviously it will be unambiguous. So obviously it will be ambiguous language. Okay. Yeah. So I hope I have made the point clear. So for regular and DCFL, it will be trivially decidable because these are always unambiguous languages. But for CFL, maybe ambiguous or unambiguous, and there is no algorithm for checking. So for CFL, CSL, REC, and RE, it will be undecidable. Okay. Next. So see here, I have given you a table. So you have to remember this table. Okay. And I will give you, if you are feeling uncomfortable, then I am giving you a small hint. For regular, each and every problem will be decidable. For DCFL, these four are decidable. Subset is undecidable. Disjointness is undecidable, but rest are decidable. For CFL, membership emptiness is decidable and finiteness is decidable. Rest all are undecidable. And just try to you can say recall the proof. For emptiness, why it is decidable because useless useful, and finiteness also useless useful. I have given you a small hint. Okay. So for CSL, only one is decidable, that is membership. For REC, only one decidable, that is membership. RE, no problem is decidable. Each and every problem is undecidable for RE. Okay. And in fact, this is nothing but your Rice theorem itself. Rice theorem says any non-trivial property or any non-trivial portion of RE languages is undecidable. Okay, so don't worry, I will tell you Rice theorem in this lecture itself. So I will come to it. Don't worry about it. So I'm just giving you a hint that this is according to this can be done by Rice theorem also, that for RE language all these problems are undecidable. Okay. So yeah, so I just want to say that for regular each and everything is decidable. For RE none is decidable. For REC only membership is decidable. For CSL only membership is decidable. DCFL and CFL you have CFL already remember by proof. For DCFL you just have to remember subset and disjointness is undecidable. Rest all are decidable. That's it. Okay, so it's your own choice how you make the make things easy for yourself. So but the only thing is you have to remember this table. That's it. Okay, so I'm jumping to next slide now. So next is 6 undecidable problems of Turing machines. So first is halting problem, then blank tape halting problem, then state entry problem, RE membership problem, PCP and MPCP. Okay. So these are 6 problems. Please note it down fastly, and I'm jumping to next slide. Yeah. So first is halting problem. Halting problem says given any Turing machine M and a string W, while processing W, M will halt. This is the problem. Okay. So we have a Turing machine M and a string W. While processing this W, M will halt. This is the problem. This is known as halting problem. And it was one of the first known undecidable problem. First known undecidable problem. And I'm not going into proof of it because proof is very difficult. And obviously it is a basic course. So I'm not going into proof. You have to remember. See, I have already told you 6 undecidable problems. Undecidable. So halting problem of Turing machine is undecidable. So just try to remember the statement. What halting problem says, given any Turing machine M and a string W, while processing W, M will halt. That is halting problem. Okay. Next is blank tape halting problem. It is modification of your halting problem. It is just saying if an arbitrary Turing machine is started on a blank tape, if an arbitrary Turing machine is started on a blank tape, will it eventually halts? This is blank tape halting problem. Okay. Yeah. So how will you prove blank tape halting problem is undecidable? See, this is very simple. I will try to reduce halting. I will try to reduce halting problem to blank tape halting problem. Okay, and obviously I will be able to reduce it. And how reduction is done? It is beyond the scope of this course. I'm just giving you a hint. And the question can be directly asked in GATE as well as NET that halting problem is reduced to blank tape halting problem. What does this mean? This means that, see, we know that halting problem is undecidable. So blank tape halting problem is reduced to it. That means what? BTHP, blank tape halting problem, is at least as hard as halting problem. So blank tape halting problem will be undecidable. Okay, so if given problem is undecidable, then if this is reduced to another problem, then it will be undecidable only, because blank tape intuitive idea is because halting problem is reduced to blank tape halting problem, so blank tape halting problem will be at least as hard as halting problem, and we know halting problem is undecidable, so blank tape halting problem will be undecidable. So how will you prove blank tape halting problem is undecidable? Just reduce halting problem to blank tape halting problem. Okay, yeah. So please note it down. I'm jumping to next slide. Yes. Now this is a very important question. Many times questions has been asked from this topic. See here, how to prove any problem is decidable or undecidable. Okay. So first is undecidable. So you just try to reduce a non-undecidable problem. Reduce non-undecidable problem. You did to your problem. Okay, you have invented one problem and you want to prove that it is undecidable. So you have to reduce a non-undecidable problem to your problem. Then you will say your problem is undecidable. Okay, so KUD, non-undecidable problem, is reduced to your problem. YP, your problem. Then what will you say? This is your undecidable. So you will say that it will be undecidable. Okay, why? Because I have already told you that your problem is at least as hard as your non-undecidable problem. Hence, your problem will be undecidable. Now, how will you prove that given problem is decidable? This is again very, very simple. Okay, so your problem, this is your problem, and you will try to reduce or you can say you will, okay, let me say like this. Your problem, you will reduce your problem to a non-decidable problem. Okay, so you have reduced your problem to a non-decidable problem. Okay, non-decidable means what? This problem is already known to us that it is decidable. You already know the fact that this problem is decidable, and this may be any problem X, Y, Z. We really, it hardly matters to us. The main thing is it should be a non-decidable problem. KNOW unknown. Okay. non-decidable problem. If you are comfortable in Hindi, then I will say Jani Pehchani problem. Okay, yeah. So non-decidable problem, and you will reduce your problem to this problem. So you will say what? This is decidable. So your problem will be what? Less harder than KD. So that means what? Your problem will be obviously decidable. Okay. So I hope I have made the point clear. So just to summarize, I will say P1 is reduced to P2. P2 is undecidable. What can you say about P2? Similarly, P1 is reduced to P2. P2 is undecidable. What can you say about P1? P1 is reduced to P2. P1 is decidable. What can you say about P2? P1 is reduced to P2. P2 is decidable. What can you say about P1? 4 questions you have to answer. Question number 1, question number 2, question number 3, question number 4. Let me use a different color here. P1 reduced to P2. P1 is undecidable. P2 will be what? P2 will be at least as hard as P1, so it will be obviously undecidable. Now, this see here. See here carefully, otherwise it will trouble you a lot. Please see here carefully. P2 is undecidable and P1 is reduced to P2. What can you comment about P1? P1 will be less harder than P2. How much less harder? We do not know. So I cannot comment about it is decidable or undecidable. Next question, P1 is decidable and P1 is reduced to P2. So P1 is decidable. So P2 will be more hard than P1. How much more hard? We do not know. So no comment. It can be decidable or undecidable. P1 is reduced to P2. P2 is decidable. So P1 will be less harder than P2. So obviously it will be decided. Please note these questions. Okay, please, if you are not able to follow, rewind the video and watch it again. Otherwise, you will get confused and it will really trouble you a lot. Okay, please note it down carefully, all these things. Yeah, so now I am jumping to next slide. Next is state entry problem. State entry problem says given a Turing machine M and a string W, while processing W, M will enter state Q. This is state entry problem, and this is also one of the undecidable problem of Turing machine. I have already told you I have given you a list of 6 undecidable problems. 2 are over. This is third. First was halting problem. Second was blank tape halting problem. Third is state entry problem, and this is also undecidable problem. Why it is undecidable? See, think about it. If you think that it is decidable, if this was decidable, then I will obviously say that halting problem is also decidable. But halting problem is undecidable, hence this will be undecidable. Okay, so let me show you one thing. Only I'm not going into detail. I'm just giving you a small hint. I am saying that if this state entry problem was decidable, then your halting problem will be decided. But we already know that halting problem is undecidable. Hence, this should be undecidable. This is the way to prove how state entry problem is undecidable. And I'm just giving you a small hint. See here carefully. See, if this was decidable, if state entry problem was decidable, so you may think that the Q is the only state which is a halting state. Okay, so directly and indirectly, what you are saying that while processing W, this Turing machine M will halt or not. Okay, so obviously this problem is you can say reduced to halting. Halting problem is reduced to this problem. Indirectly, I'm saying it like this. Okay, so if you are able to follow, then it's okay. Otherwise, just try to remember the fact that this is undecidable problem, and this is a well-known undecidable problem. Okay, again, I'm not going into proper proof and all because this is a basic course. No, this is not advanced course. Okay, so I have given you a small hint also that halting problem will be reduced to state entry problem. Okay, or just see, actually I'm not able to control myself, so I'm just giving you a very small hint. See, there can be many states. Okay, and all these states may you can say from all these states we can have a move to a halting state. Now I will say, I will label this state as Q. Now I will say that this is Turing machine M and this is a string W. While processing W, M will enter this state Q or not. So if M enters this state Q while processing W, M enters this state Q. This directly and indirectly means that I am saying that while processing W, M will halt or not. Okay, so this is the main thing. So now I'm jumping to next slide. Next is RE membership problem. I have already told you that given a Turing machine M and a string W, M accept W. This is the question. See, directly and directly, again, it is saying like a halting problem only. M accept W. M accept W means what? M will halt on W. Okay. So hence it will be undecidable. I have just given you a small hint and I'm not going into detail. So this RE membership problem is nothing but this only. Okay, so see here, RE membership problem, RE membership problem. Okay, so directly indirectly I have now given you a small hint that why membership problem of RE is undecidable. Because if this was decidable, then halting problem will be decidable. But we already know that halting problem is undecidable. Hence, this will be undecidable. Okay, this is the way to prove. Okay, so again, I'm not going into proper proof. I'm just giving you a small hint. So M except W means what? Directly, indirectly, we are saying that M will halt on W. But we already know that we cannot say that M will halt on W or not, because for accepting it must halt. So I hope I have made the point clear. So this is RE membership problem, and it is again undecidable problem. Okay, so and why I'm saying it as it is one of the undecidable problem for Turing machine, because I have given you hint about Turing machine only in this problem. Yeah, I am jumping to next slide. PCP. PCP is post correspondence problem. Post correspondence problem say, see, we have two lists of numbers, and the condition is that we have to use one number. Like if I choose one, then from list one I will take see, from list one if I choose one, then I have to choose one from list two also. If from list one I have chosen number two, then from list two also I have to choose number two, and so on. Okay, so now what exactly is this problem? We need to find a solution to this problem. So for this problem, solution means, see, if I apply number two, then from the list one I will write one. Let me write here 2. So from the list one I will write 1. From the list 2 I will write 111. Okay, now I am sorry for that, 2 na 2 means what? From list 1 I will write 10111. From list 2 I will write 10. Now I am choosing 1 means what? From list 1 I will write 1, and from list 2 I will write 111. Okay, so and again I am choosing 1. Please, if you are not able to follow, have patience. I am just giving you a small hint. List 1 I will take 1. From list 2, okay, actually I'm not able to write in sequential manner. Okay, so let me do it properly, or let me take like this. From list number 1, okay, actually it is very light, so let me take like this. Okay, so from list 1 I am choosing number 2. Number 2 means what? From list 2 also I have to choose number 2. So 10111. Below that I will write 10. So these are the numbers from list number 1. These are the numbers from list number 2. And I have chosen 2 means what? I will write from list 1 I have choose number 2, and from list 2 also I have to choose number 2 only. Now 1 means from list 1 I will take 1. From list 2 I will take 111. Again I am choosing 1 means from list 1 I will take 1, and from list 2 I will take 111. Now I will take 3 means what? From 1 I will take 10, and from 2 I will take 0. Now see here, the strings have been matched properly. See, the strings have been matched properly. So we need to find one such sequence. If even one such sequence exists, I will say it is yes instance of PCP. This is yes instance of PCP. Okay, so please note it down carefully. So in PCP, what we are going to do is, we have two lists of numbers, list 1 and list 2. Condition is that you have to choose same number, and you try to derive same string. If you are able to derive same string, then we will say that this PCP problem has a solution. Otherwise, it does not have solution. So yes instance of PCP means this PCP instance has solution. So solution exists. And what is the solution? 2113. That's it. Let's jump to the next slide. So this is homework for you. You will prove, and I am saying that it is no instance. You won't be able to find any solution for it. Okay, so if you think that you will be able to find solution, then let me show you something. You cannot start with 2, because 2 means what? 011. Okay, so if you apply 2, so from list 1 you will take 011, and from list 2 you will take what? 11. So there is mismatch in the starting itself. Okay, and if you want to start with 3, then obviously I will say if from the list 1 you will take 101, from list 2 you will take 011, and in starting itself there will be a mismatch. So the only possibility is you have to start with 1. So if you start with 1, then from list 1, from list 2, from list 1 you will take 10, from list 2 you will take 101. So now from list 1 you need 1 here, you need 1 here. From list 1, how will you take 1? Either this way or this way. If you take this way, that means you apply 3, then from list 1 no doubt you will get 101, and from list 2 you will get 011. So again there will be a gap here, same one. So again you have to apply, and so please it's your homework and it's really not important. I'm just telling you, or I'm just giving you a hint about PCP. That's it. Okay, so please note it down carefully, and I'm saying that there is no solution for it. Okay, next slide. So it has been proven, it turns out that membership problem is reduced to PCP problem. And membership problem of your Turing machines, sorry, membership problem of your RE, membership problem of RE. See here, fourth problem, it is undecidable, and since it is undecidable, so obviously PCP will be what? Undecidable. Okay, yeah. So MPCP is modified PCP. M means modification or modified PCP. So here we have a condition that you always have to start from 1. Okay, so see here, in this solution I have started with 2 now. I have started with 2, but in MPCP we cannot start with 2. There is a restriction that we have to start with 1 only. Okay, yeah. So this is MPCP, and obviously it is similar to PCP only. Okay, and it has been proven that membership problem is reduced to MPCP, and MPCP is reduced to PCP. From these 2 points, we conclude that membership problem is reduced to PCP. Okay, so directly indirectly, I want to say here, you may be wondering that why, sir, you have told MPCP. MPCP has a, you can say, very important role in MPCP has a very important role in proving of PCP is undecidable. How MPCP is showing PCP is undecidable? I am saying that membership problem is actually reduced to MPCP, and this MPCP is reduced to PCP. So from transitivity, this is reduced to this, this is reduced to this. So directly indirectly you will say MP is reduced to PCP. So now, and you say MP is undecidable, so PCP will be undecidable. This is the way to prove PCP is undecidable. Okay, so I hope I have made the point clear to all of you. Actually dogs are barking, so please try to concentrate on my voice. I cannot control them because these are street dogs. Okay, yeah. So next, so last is Rice theorem. Rice theorem says that any non-trivial question regarding RE languages is undecidable. Any non-trivial question regarding RE languages is undecidable. Any non-trivial question. So that means directly and directly I'm saying you is, think of RE languages as black box. That is, you cannot see what is inside. So you just try to imagine RE languages as a black box, and you cannot see what exactly is inside it. So in whatever question you want to see inside the RE language, in any question, if you want to see inside RE language, you will directly say by Rice theorem it is undecidable. Okay, so see some examples. First example is, does the string 010 belong to given RE language? We have a RE language and we want to and we are asking a question that, or there is a problem that we want to say that 010 belong to this RE language. So obviously this 010 may belong to RE language or may not belong to RE language. That means we have to dive deep into it and we have to check it out. This is your RE language. You have to check it out, and you have to go deep inside it and you have to check it out 010 is present or not. So by Rice theorem, I will say that it is undecidable. Does the given RE language empty? Again, RE language is given to you. You have to dive deep into it and check if any string is present or not. So again, it is undecidable. Does the given RE language regular? Again, you have to dive deep and check it out whether it is regular or not. It is undecidable. So see, this is non-trivial question. Non-trivial means answer may be yes or no. Trivial means answer is always yes or always no. Okay, so if you are confusing about trivial or non-trivial, I will tell you small thing. Trivial means what? When can you say question is trivial? Trivial means what? Answer is always yes. Yes always or no always. without seeing anything. You will blindly say always yes or always no. Don't worry about it. I will give you some examples of trivial question also. And non-trivial means what? Sometimes yes and sometimes no. Non-trivial means what? Non-trivial means what? Sometimes yes, and sometimes no. Okay. So I hope I have made the point clear about what exactly is trivial and what exactly is non-trivial. So all these are undecidable problems. Okay. So in place of cross, I should write UD. UD means undecidable. Undecidable, undecidable, undecidable. Next, does the given Turing machine accept string 010? First and fourth question are similar. So I am saying that given Turing machine what? Turing machine accept what? RE languages. So directly and directly, I am saying that the language accepted by Turing machine is some language L, and in that L, 010 belong or not? So that means what? Again, for the please note it down carefully. This question is not about Turing machine. This question is about language accepted by Turing machine, and that is nothing but RE. So and Rice theorem is all about RE languages. See here carefully. Any non-trivial question of regarding RE languages. So Rice theorem is not about Turing machine, it's about RE languages. Okay, yeah. So does the given Turing machine accept 010? So directly and directly, I'm saying you that language accepted by Turing machine contains this string this string 010 or not. So again, it will be undecidable because the answer may be yes or no. You have to dive deep and check. Similarly, does the given Turing machine accept empty language? So again, undecidable. So this and this same question. Okay, given RE language empty. So Turing machine. So Turing machine will accept some RE language. So I am saying you that is this RE language empty or not? This is undecidable. Next, does the given Turing machine accept regular language? Again, it is undecidable because you directly and directly want to say that the given RE language regular or not. So third and sixth question are same. Okay. So by Rice theorem, all these are undecidable. Now next, let's jump to the next question. So does the given Turing machine accept RE language? This is a trivial question. This is a trivial question. Answer is always yes. Always yes. So you just give me a Turing machine. I will blindly say yes, 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 yes. That's it. So obviously it will be decided. Okay. Yeah. So again, it is not according to Rice theorem. It is obvious. It is will be decidable. Okay. So please do not say that by Rice theorem it is decidable. Rice theorem is all about undecidability. That any non-trivial question of RE languages will be undecidable. That's it. So it's not saying that any trivial question of RE language will be decidable. It is obvious. Every trivial question of RE language will be decidable. Okay. Yeah. So trivial question means what? It is not a question. Actually, it's just a, you can say, it's always yes or it's always no. So it's not at all a question or it's not making any sense. Trivial. It is a trivial. Okay. Next, does the given Turing machine has 10 states? Again, this is a question about Turing machine. It is not about RE language. So here you cannot apply Rice theorem. By the way, I can tell you that this problem is decidable because you can obviously count the state in any Turing machine. Obviously, you can count the state. I have given you a Turing machine. You can obviously count the states, so it will be decidable problem. But it is not the question of Rice theorem because Rice theorem is all about RE languages. It is not about Turing machines. Okay, so I hope I have made the point clear. So that's it. This is all about your TOC subject. And let me show you one thing. One thing is coming into my mind. See here, I have told you that by Rice term all these will be undecidable. See, membership means what? Any string W belong to L or not. So you have to dive deep into the L and say whether this W belong to L or not. So again by Rice term it will be undecidable. Emptiness, again by Rice theorem it will be undecidable because you have to dive deep into RE language and check, because I have already told you Rice theorem says that any non-trivial question about RE language is undecidable. Any non-trivial question means what? You cannot you cannot dive deep into RE language. That means this is just like a black box. So completeness problem, again it is nothing but sigma star. So sigma star means what? Each and every string should be present in the language. So again, each and every string may be present in the language or it may not be present in the language. So directly and directly, what I want to say is you have to dive deep into it, and I cannot dive deep, so hence it will be undecidable. Equality, two RE languages are given. So obviously, without getting deeper into them, how can you decide that both these languages are same? You have to dive deep into it and dive deep into it also. but we cannot do it because these are just like black box. So by Rice theorem, it will be undecidable. Okay, equality will be undecidable. Subset again undecidable. You can check it out. Disjointness and so on. Okay, so I hope I have made the point clear. So Rice theorem just it's saying that you cannot dive deep into it. That's it. This is a rough idea. Of course, I'm not going into proper mathematical details and mathematical equations of Rice theorem and so on, because that is out of scope of this course. This is a basic course. Na? In advanced course, don't worry, I will tell you about it. Okay, so that's it. This is all about POC. Thank you so much. Best of luck to all of you. If you are able to follow all these lectures, then you will be able to solve all the GATE, all the NET, UGC-NET exam questions, and obviously your semester exams can be you may be able to get full marks in semester exam also if you have watched my lecture properly and make proper notes. Okay, thank you so much. Bye bye.